잘 들리십니까? Can you hear me quite well? 잘 들리십니까? Can you hear me? So can you let me know whether the sound is good or not? 네, 감사합니다, 유아영 학생. Thank you for your response, 하영 유. So let me start the class today. So today, 네, 감사합니다. So today we're gonna talk about the research topics in Korea University School of Electrical Engineering, Communications, Networks, and RF. So today, let me make a presentation. So in this presentation, I would like to let you know my research topics in Korea University School of Electrical Engineering. So in School of Electrical Engineering, Communication, Networks, and RF, we have a lot of topics over here. So basically, we can classify the research topics as follows: system, network, and AI and deep learning. First of all, in systems, we have big data platform, UAV, and autonomous driving. And in networks, we have streaming, 5G and 6G, and security and privacy. And lastly, in AI and deep learning, we have deep learning network applications and GAN and CNN and multi-agent deep reinforcement learning and econometric theory. So let me go with the topics one by one very deeply. So first of all, I would like to let you know we have the topics in learning-based objective moving objects. So in this topic, we have two subtopics. The first one is reactive control for learning-based system. The next one is deep reinforcement learning for vehicles. So let me go with the first one here. So in real world, we have a lot of problems. So among the problems, we have a lot of formulation with utility maximization. For the utility maximization, we have linear programming and complex programming over there. So, but in this case, for this programming or optimization framework, we have no consideration on time. But suppose that our solution introduces delay. And if we choose this optimal solution every single time, it would be very harmful for real-time mobile systems. That's why we can think that we have a trade-off between the utility and delay. So in order to model the delay, we have these kinds of concept, time modeling. So for this purpose, we have to model the time with Q, and then we have to do the reactive drift formulation with the Q values. Then finally, we can do the time average optimization on the Q stability. So this is the main objective of our research. So here, every single time we have to make a formulation for the utility maximization. That's why we have to consider the energy efficiency, quality maximization, PSNR maximization, accuracy maximization. But all these utilities should consider the delay. That's why we have to do Q-based model here, okay? So we have trade-off between them. So every single time, if the delay is not a problem at all, then we have to consider utility maximization. But if the delay is very important, then we have to consider both of them. That's why we have to consider this trade-off for the optimization. So suppose that we have mobile system. So in the mobile system, we have processors. And when we work with the mobile system, then every single time you're gonna make a task over there. So then when you touch your touch screen, your mobile system, then in the case, you will gonna make a lot of tasks in the mobile system. Suppose that you are using KakaoTalk, YouTube, Facebook, then you're gonna make a lot of tasks to be processed in the application processor. Then that is called task queue. Okay. So suppose that you have a lot of tasks over here, then you have to process the task in here by this processor. But if you allocate more and more cores in this processor, then in that case, you will process this one faster. Then it will be good in terms of the stability. However, it's not good in terms of energy consumption. Okay. But if you allocate less processor here, then in the case, your energy consumption is very small. That's why it's good in terms of energy efficiency. However, it's not good in terms of the stability. Okay. That's why you have a trade-off between the energy efficiency and the stability. Okay. So that's why you need some mechanism which can control the trade-off between them. So in this case, you have another problem that is called wireless video streaming. Okay. So in this case, you want to design an algorithm which can maximize the time average video quality subject to queue stability. So this is your queuing system. This is your transmitter. This is your receiver. You want to transmit your signal from here to here. In that case, you will put the stream one by one here. Okay, because based on these streams, suppose that you have 100 streams here, and that is for the video streaming. Okay, you will allocate the stream one by one. Then in this video streaming, you can control the quality one by one here. That's why you have a quality controller. Okay. So in this case, if this quality is link quality is very good, then in the case your departure process here in the queue is very faster. That's why you can allocate one by one here, and then you can control the quality one by one here. So if this one is full here, then you have to compress a lot in order to avoid a queue overflow. However, if the queue is idle, in the case you don't need to compress a lot because you want to maximize the uh, video quality. That's why you have a trade-off between the quality and stability. That's why you can use this formulation. Okay. So another topic is adaptive deep super resolution neural network. So this is a kind of deep learning application in mobile systems. Suppose that you have drone or UAV here, and you have mobile edge computing platforms here. Okay, then you can transmit the video here to here. So in that case, you have images, and then you have to compress a lot in order to handle the unexpected situation in this channel. And then this small amount of image can be transmitted to this mobile edge computing. And then the MEC can receive this signal, and then it can decode it, and this should be improve its quality based on this neural network. So in this case, the entire flow is as follows. So you have image and you have to compress a lot, and you can transmit it, and then you can recover the quality based on this deep learning architecture. So this is the entire process here. So in this case, this traffic should be very bursty because in this case, this drone compress a lot. That's why the quality here is not that good. But this the arrival traffic in MEC mobile edge computing should be bursty because the communication between the drone and MEC is not that stable. And in the case the arrival at the MEC should be random arrival. That's why sometimes it should be very idle, sometimes it should be very bursty. But if it is bursty, it means that it will introduce a certain amount of queuing delay. That's why if it will gonna introduce a lot of delays here, then in the case your processing should be very faster in order to avoid the queuing overflow. That's why in the case you have to use the neural network architecture, which is very faster, even though the performance is not that good. On the other hand, the queue is very idle. Then in the case, you can use deep neural architecture, which can improve the accuracy a lot, even though it takes a lot of time. Then you can imagine that there is some trade-off between the time and the performance. So here, if you have more and more hidden layers here, then it means that if you have more and more hidden layer here, it means that you have highest PSNR quality, even though it takes a lot of time. That's why in this table you can imagine that you can observe that there is trade-off between the time and the accuracy. That's why you can observe the trade-off between them. So lastly, you have these kinds of backbone models, and then you can choose one neural network architecture, depends on the queuing delay in the mobile computing device. So here, and then you can design a new neural network architecture which can take the result in the middle of the process. So in the case if you have some delays in the here, in this mobile computing, if the delay is very high, then in the case you can take the result in the middle of the processing because you want to avoid queuing delay because you want to save the time. But if your queue is very idle, then in the case you can process this neural net architecture until the end, then you can guarantee certain amount of delays, even though it takes a lot of time. That's why you can observe the trade-off between them. Okay. So this is the overall logical architecture we have. So you have queue here, and you have random arrivals into the queue. And then if the queue is very bursty, it has a lot of packet here, then you can take the neural network architecture, which is more complex and faster. Then you can process the packet faster than the others. But if the queue is idle, then you do not want to consider the queuing delay a lot. You want to achieve your main purpose that is called accuracy. That's why you have to choose the neural network architecture, which has a higher accuracy, even though it is very slow. That's why you can adaptively select the neural network architecture based on this set. So in this case, our proposed algorithm is a black curve. If it is stable and if the neural network is uh, very faster, but it has small amount of very faster, but it is very its accuracy is not that good. Then in the case, you can see that the you can see that the performance is in a blue curve. So in this case, your stability is good because your stability is good because it takes a lot of it because it processes a lot of bits because it's faster. But as you can see here, the performance is not that good. But when you look at the red curve, then it means that it takes a lot of time to be processed because it takes a lot of time in order to process it. However, the accuracy is very good. But in our proposed algorithm in black curve, it goes in the middle of the process, in the middle, but it is stable as well. That's why it's the best solution among these given three. But up to now, we studied about the control in the departure process, but now you have a control in arrival process in the queue. So in the queue, we will control the arrival process. So departure process is given is open face based face identification process. But if the queue is but if the processing can be random arrival because it takes face identification framework takes some time, depends on the number of faces in the images, but the number of faces in the image can be varying. That's why it is random arrival. That's why sometimes the queue is very bursty, the queue is very idle. It depends on the number of faces in each image. That's why if the queue is very busy, then in the case you have to control the CCTV camera in the arrival process, and you can slow down the sampling rate. But if the queue is very idle, then in the case you can increase the sampling rate in order to improve the accuracy of the CCTV camera. That's why here we have to do sampling rate selection based on the network optimization. The next topic is deep reinforcement learning. So in deep reinforcement learning, you can control the actions every single time, given a state or even given observation. Okay. So here we have one algorithm that is called imitation learning, which is widely discussed in ICML several times. So it's very hot topics nowadays in the society. So here in our lab, we have some algorithm that is called propofol infusion control. Infusion control in the medicine, especially in anesthesia. So in that case, we have to control the infusion of the propofol or fentanyl based on the human body behaviors. That's why we will observe BIS and blood pressure, and then we will control the number of propofol and fentanyl in order to conduct anesthesia-based functional test. That's why we're gonna make the reinforcement learning algorithm based on this data. So that's one thing we are studying in our lab. So in addition to that, we have some research in autonomous driving. So we have a lot of implementation that can control the behavior of the vehicle control, given situations or observation. That's one thing we are studying about in this research. The next one is multi-drone coordination for 5G coverage extension. So in 5G, we are using a millimeter wave. But in millimeter wave, as you can see in this illustration, the propagation is directional and that's why we have a lot of package areas. That's why we have to use the UAV in order to extend the coverage. Then you have to use multiple UAVs. That's why we are using deep reinforcement learning based multi-agent navigation. So here we have two UAVs. So you have red UAV, you have green UAV. So two UAVs are flying, and then we have blockage here, black things. So this signal from the middle cannot go through this wall. That's why you have to use these UAVs in order to send the signal behind the wall with one delaying. So this is called a UAV coordination for 5G network coverage extension. Okay. So next one is privacy preserving deep learning for geodistrict medical clouds. So so in deep learning computation, we will gather all the data in a central devices. But in the case, we have medical applications and mobile applications. Gathering all the data in a single space is not easy in medical platforms and mobile platforms. In medical platforms, it's not easy because sharing the patient data is not allowed by the law. That's why we have to keep the privacy for the individual patient. That's why in medical platforms, we have to conduct the deep learning computation in each hospital at first, and then we will gather the parameters from the hospitals into one space in order to generate a global model. In the mobile platforms, gathering all the data is not allowed. Is is possible. It's not is possible. However, it takes a lot of overhead. That's why we have two different motivations. Here in the medical platforms, we have to keep the privacy of the individual patients. In mobile platforms, we have to avoid the communication overhead and reliability. And we have to keep the reliability. Based on these different motivation, they have to conduct deep learning computation in a distributed manner at first, and then we will get all the parameters into one single space. So that's why we have to study about federal learning. Okay. So, but it's not easy because in each uh, distributed computing devices we have data imbalance. That's why overfitting can be a problem because it has 1,000 data here, it has only 10 data here, only 10 data here. So models in this yellow devices is not that accurate because it has small number of data to train. But here in green, you have a lot of data here. That's why you can make a very nice model. So when you converse all the data into one space, then the performance will be lower than this green one. That's why this is one thing we have to consider in federal learning. So when we have a lot of individual local models in device K, so in the case we have to get all the data in this edge server, and then we have to make average in order to generate global model. But this is very intuitive and easy approach you can consider because this is just a simple averaging operation based on the given data. Okay. So taking the average of individual weight is not good when overfitting happens, as I told you before. That's why we need a lot of topics. We need a lot of research here. That's what we are studying in our research lab. So federal learning averaging is very intuitive. That's why we need to consider a lot of algorithms. So nowadays in our lab, we are consider the case where we are using attention model on top of these individual devices. So up to now, we introduced a lot of research topics in my research lab. The first one is delay-based learning system implementation. The next one is deep reinforcement learning for the vehicles. And then lastly, we talked about the distributed deep learning computation for medical applications or communication applications. So these are the research topics, what we are doing nowadays. So if you have questions, please let me know. Then I can answer to you one by one. Or you can leave your message in the chatting room and I can answer to you. 자, 질문 있으시면 질문해 주시면 제가 음성으로 답변을 드리거나 아니면 채팅으로 답변을 드리도록 하겠습니다. 말을 좀 빠르게 해가지고 좀 양은 많은데 일찍 끝났습니다. 그래서 질문 있으시면 하나하나 제가 답변을 드리도록 하겠습니다. So actually, I present this material faster. That's why even though the slide we have a lot of slides, more than 30, it it finishes faster than the others. So if you have any questions, then I can answer to you one by one. We have some time. 예, 이나연 학생 질문 답변드리겠습니다. I will answer to you questions by one Korean students. So in the system, we will gonna process the given task one by one, and then we are using the queue. But can we use the other data architecture? That is the question by one Korean students. 자, 이나연 학생 저기 보시면 알겠지만 이게 시간이 지남에 따라서 뭔가 스토리지에 데이터 많이 쌓인 거잖아요. 그러면 그게 오버플로우가 나는 걸 걱정하기 때문에 우리는 그거를 시간에 따른 모델로서 Q를 써요. 근데 만약에 이거 스택을 쓴다든지 뭐 다른 구조를 쓴다 하더라도 크게 상관이 없어요. 왜냐면 우리가 그 시스템 안에 얼마나 많은 데이터가 있느냐가 중요한 거예요. 그래서 만약에 시스템 안에 데이터가 너무 많다. 그래서 정확도나 뭐 에너지 효율성이나 우리가 추구하는 목표를 우리가 계속 동작시키는 것보다 그런 것보다 우리는 빨리 프로세스 해 가지고 그 스토리지가 터지는 걸 막는 게 더 중요한 상황이 와 버린다면 그러면 액큐레시 보고 다 포기하고 빨리 프로세스를 하는 거거든요. 그렇기 때문에 그 시스템 안에 있는 데이터 양이 중요한 거지 정확도가 그렇기 때문에 꼭 큐를 쓴다는 건 아닙니다. 그래서 우리는 스택을 쓸 때도 있고 다른 여러 가지 데이터 스트럭처를 쓸 수 있지만 우리의 퍼포스는 뭐다? 우리의 퍼포스는 뭐냐면 어 그 양을 재수만 있으면 돼요. 그래서 큐를 사용하는 거는 어 그 안에 있는 양을 보기 위한 거고 또 일반적으로 우리 운영체제나 네트워크 시스템에서 우리 큐를 써야지 그 어라이벌과 디파처를 정의할 수 있기 때문에 쓰는 거지 그 양만 보면 되니까 뭐 스택을 써도 되고 다 상관이 없습니다. My answer is that we can use a lot of data structure for that. So at least we have to measure the amount of the packets in the system. So then if the amount of the packet is very high, so we will nearby the overflow situation, then we have to consider the processing of the packets seriously, mainly instead of our utility maximization. That's why if we can measure the amount of the packets or data inside the system, that'll be enough. That's why you can use the queue, you can use the stack. It's up to you. You don't need to worry about that too much. However, however, at least you need to measure the amount of data. That should be enough for us. Okay? That's why you can use the queue, you can use the system. It's up to you. 예, 이남 학생 좋은 질문 감사합니다. Thank you for your good questions here. 예. 오늘 저희 강의는 제가 전반부에 30분 동안 강의를 하고요. 후반부에 30분 동안 전상근 교수님께서 강의를 하십니다. 그래서 저희는 9시 30분에 전상근 교수님께서 RF에 대해서 이제 RF나 테라스 통신이나 여러 가지 최신 통신 시스템 설계 및 물리계층에 대해서 설명해 주실 거예요. 그래서 그때 전상근 교수님께서 좋은 말씀 해 주실 것 같습니다. 5분 후에 시작할 것 같습니다. So after 5 minutes later from 9:30 Professor Sang-gun Jeon will gonna make a presentation for the other part. So that is related to RF and antenna system design and implementation for next generation cellular systems. So that will be very interesting. So I hope you will enjoy the presentation by the professor. Okay. So if you have no further questions, then I will let Sang-gun Jeon, Professor Sang-gun Jeon knows our class is over. So you have to stay here. Okay. He will gonna make a presentation from 9:30. Okay. 여러분, 전상근 교수님께서 저랑 전상 교수님 둘이 강의를 하는데 전상 교수 오전에 강의를 하셨대요. 저랑 동시에 저는 지금 줌에서 강의하고 있었는데 전상 교수님 콜라보에서 강의를 하셨다고 하네요. 그래서 이 전상 교수님께서 말씀하신 내용을 여러분께서 못 들어서 너무 죄송한데 이걸 제가 어떻게든 뭐 서머리를 한번 요청을 하도록 하겠습니다. 그리고 오늘 강의한 거는 제가 녹화를 해놨으니까 녹화한 내용은 제가 이제 유튜브에 올려놓고 여러분께서 유튜브에 들어가서 이 강의를 보실 수 있도록 복습을 하실 수 있도록 만들어 놓겠습니다. So Professor John told me that he also made a presentation from 9 to 9:30. That's why we overlap. That's why we have no chance to hear to his research topics and results. But you can review the result here, okay? So I will post this. 유하영 학생, 그러니까요. 전상훈 교수님 파트 녹화 영상이 있는지 한번 여쭤보도록 하겠습니다. 저한테 이메일 유하영 학생, 여기 밑에 보시면 하단에 보시면 제 URL 있죠. 일로 이메일을 주시면 제가 한번 전상훈 교수님께 여쭤보도록 할게요. 그래서 링크가 있으면 보내드리도록 하겠습니다. So I will gonna post. 예, 감사합니다. So I'm gonna post this presentation into my YouTube link, and I will share the link in our announcement, and you can review what I have presentation here. Okay. So thank you for your participation today, and we're gonna meet all together next time. Thank you.